Thank you for the introductions. My name is Ning Yan. So we're going to talk about the high frequency resonant converter today. So I'll start with the background and motivations, and then talk about the topology designs and considerations. And then I will give you a brief introduction to the hardware design and show you the hardware prototype and test results, and then conclude this presentation and give you some future works. So first is for the background. There are for applications like solar panels, batteries, medium voltage converters. They will require some isolated DC-DC converter to serve as the power supplies for power optimizer, battery charger, also power supplies for like gate drivers. So today, it will be our today's focus. So for such DC converters, it will require isolation capabilities with minimal size. And because of the the application, the variation, the voltage variation for the applications, it will require have a wide input voltage range with fixed output. At the same time, with step up and step down capability. And then to avoid any thermal issues, we will prefer high efficiency. The challenges are one associated with the circuit design and one is with the hardware. So transformer as the conventional isolated components, they normally they're normally the most volume occupied components. So people tend to increasing the frequency to reduce the volume. As you can see for the few examples here, so you get more benefits up to 1 MHz, but after 1 MHz, because the core losses start increasing quite a lot, they stop using core-based transformers. But of course, you can use the wireless power transfers, but in that case, you lost the compactness of the design. Another transformer challenges will be the insulation designs. So as you can see that there are many insulation designs like to increase the insulation voltage. But in general, when you start increasing when you have a higher and higher insulation voltage requirement, your overall size will be much larger. And also the complex insulation design is often required. So the question is, can we achieve isolation without transformers? So as alternative method, capacitor isolation serve the same functions. As you can see for the 1 nanofarad capacitor examples, the ceramic capacitor can go up to 10 kV with very small volumes. And because the simple design of the capacitors, you can actually easily just stack them in series to double the insulation voltage. So which simplify the insulation design a lot compared to transformers. So in terms of the application for the capacitor isolations, normally we have wireless EV chargers. So it will normally work below 1 MHz and have the power over 1 kilowatts. If you further push the frequencies to 1 gigahertz, people normally use capacitor isolations as medical devices. So they're used for the signal transfer. So the power is normally below 1 watts. So our work today is to is in the range in between, because currently the design doesn't have like the power requirement that fits the specs. So in terms of topologies, first we have the SEPIC converters, which is well-known converters for step up and step down capabilities. And then we have the split capacitors to serve as the capacitive isolations. But however, this converter is a hard switching converter topology, so it will have high switching loss and large capacitor values will be required for energy storage. And then to achieve soft switching, we have Class E converter, but it will have a limited voltage gain due to the series resonant network. Lastly, we have the Resonant SEPIC converter. So we have additional two capacitors introduced compared to SEPIC converters. So they will serve as the resonant component to achieve soft switching capabilities. But the drawback for this one is you will have a high device voltage stress, and we'll see that later. So brief introduction of the working principle for the resonant SEPIC converter. So first, when the device is turned on, all the inductors are charged, and the capacitor CS1 and CS2 are discharged through the device. And during mode 2, once the voltage across LR is increased large enough, the diodes are conducting. So LF will continue charging, and the LR will be clamped by the output voltage and continue supporting the output voltage. So in the next mode, the main switch will turns off. In this case, the voltage of the across the device will start increasing, and in the meantime, you will form multiple resonant loops. And in the last mode, both devices are turned off, so we'll have pure resonant transient phase. So for ZVS realization, it's very important for our circuit design because associated with switching losses. And for this converter, it's associated with the last mode. So during the last mode, the main switch is turned off. And during this period of time, as you can see that because of the resonant, the drain source voltage like naturally discharge to 0 volt. So you will have a specific regions for you to turn on. Like as long as you turn on between the negative cycles, you can achieve ZVS. So in this case, in our design, we will suggest to design the resonant frequency be above above the switching frequency and below 2 times of the switching frequency. Here shows the example for the for around the resonance frequency around the switching frequency. So you can see a perfect ZVS. That's the drain source voltage reaches 0 volt right before it turns on. However, if it failed to reach the 2 criteria, you will lose ZVS. And just give you a brief like taste for the efficiency comparisons. So you have will have at least 20% of difference for achieving ZVS and without ZVS. So ZVS is very important in this converter design. Another aspect to impact the ZVS will be the input voltage. So after you design all the components correctly, the input voltage will also impact the ZVS. So to achieve the ZVS, you want the device current IDS to be less than 0 amp. So in this case, you will want the LF current to be less than the CS1 current. In this case, at higher input voltage, you will gain a higher current ripples on LF component, and also the average current is lower, so you can achieve ZVS very easily at high voltage. However, at low voltage, such as input voltage of 10 volt, because of the small current ripples and high average current on the input side, so you will lose ZVS in this case because the current changed the direction and start charging the CF value. So next we can talk about the after finishing the circuit design, we talk about the PCB layout. So in the real hardware design will have multiple components in parallel to minimize the loss. So in this case, balanced current distribution will be very important among all parallel components. And also you want to minimize the parasitic loop inductance, especially in driving loops and the resonant loops. because you want to first prevent a gate over voltage, and also to minimize the loop inductance in the resonant loop, you can obtain a more desired performance for the converter, and the components selection will be more accurate for your design. So here is the first version of the PCB design. So it's a 2-layer PCBs, and with all the component on the top surface, and the bottom surface will just be copper layer, a pure copper layer that's designed for heatsink. So in this design, you can see that the CS1 and CS2, they are all lined up, and the positive rail and the negative rails are separate. So in this case, the power flow is from left to all the way to the right, but it has relatively long traveling paths, so which increase the loop area and PCB size. In terms of current distributions, we did the ANSYS simulations. So as you can see that on the top surface or on the top layer, you can see the current crowding issues on the traces, which is indicated in the right color. And also you see unbalanced current distribution among all the components, such as CS5 will have higher current than CS1, and then D1 and D3 will have higher current than D2 and D4. And you can observe you can see the same thing on the bottom layers. Will be current crowding on the ground plane. So to improve that, we have the second revisions for interleave configurations. So in this design, all the capacitors are placed vertically. That's the first thing to reduce the overall size. And the second, so we interleave them. So we put the positive rail which we put one positive rail capacitor next to a one negative rail capacitor to reduce the loop. So to reduce the returning loop. So in this case, all the return loops are very short and very even because they are interleaved. In addition, we add slots under the resonant inductors to reduce the shielding effects on the PCB. So overall, in this design, the input power is still from left to right, but the power path traveling is much smaller. So from the simulations, you can see that by doing the interleave design, we can achieve the balanced current distributions, and also there's no crowding issues on the PCB. This is a quick comparison for the PCB parasite inductance. As you can see that both circuit can achieve about 2.4 nanohenry driving loop inductance, and with less than 1 nanohenry resonant loop inductance. And especially for the interleave configurations, the resonant loop involving CS1 and CS2, they can be largely improved to only about 1.3 nanohenry for right now. So overall, for the interleave configurations, the footprint reduced 14%, and then we lower the loop inductance and get a better current sharing performance. So here is the hardware design examples and implementations. On the left side, that's the hardware. So we have 2 GaN devices in parallel and 3 Schottky diodes in parallel. And in the middle, that's the isolation capacitors. So for this design, we have the input voltage from 10 to 80 volt and output voltage from 60 to 80 volt. And the output power also varies, depends on the load with the max output power of 167 watts. And it's designed specific at 5 megahertz. And just once again, this is a 2-layer PCBs and with all the components on the top surface, so which makes the size a little bit larger than you thought about. Here is the steady state result for for DVS verifications, as you can see that, so from, according to the test, a DVS can be achieved for majority of cases, except the input voltage of 10 volt and output voltage 80 volt, which is aligned with the analysis and simulation we showed earlier. This is because of the low current ripple and low and high input average current. And just one thing to mention that as you can see, the device, because of the resonant, the device voltage is actually higher, like much higher than the input and output voltage. So overall, we can achieve the efficiency over 87, so with a peak efficiency of 87.7%, and this is achieved under heavy load with output voltage of 60 volt. In general, the output of 60 volt can achieve higher efficiency than the output of 80 volt condition. So overall, well, our design converter can achieve relatively high efficiencies, and that's like comparable to the 5 MHz transformer isolation designs. And we are the first one to demonstrate the power of 150 watts out and the frequency of over 1 MHz with a peak efficiency of 87%. So as a conclusions, with a 5 MHz capacitive isolation, isolated resonant SEPIC converter is proposed and achieving compact size and high efficiency. So this design support a wide input voltage range and output of 60 to 80 volt. And this deliver up to 160 watt with peak efficiency of 87.7%. So the key reasons for high efficiency is first, we achieve ZVS with across wide voltage range. And also we achieve the balanced current sharing among all devices. So we make sure we don't have thermal issues. And also we minimize the loop inductance through the interleaf PCB layout. And overall, the interleaf PCB also contribute to smaller capacitors, smaller converter size and improve thermal and electrical performance. So for the future work, if you want to further, so right now the current designs only support up to 2 kV. And if you want to further extend the design to medium voltage applications, you can physically separate the two PCBs and start stacking the capacitor in between to for higher insulation voltage level. And thank you guys.
Thanks, Ning. And we have about 5 minutes for questions. So if you have question, please approach to the microphone there, since we also have attendance online. And also please introduce yourself a little bit. Yes, please.
John Wenxiao, Warp Speed. Thank you for a very interesting result. One question comparing this capacitive isolation versus magnetic. If you want to extend this to like medium voltage, high voltage, if you have a failure for magnetic, you have the real isolation, have a physical gap. But if you use capacitive isolation, I'm afraid if you have the failure, you may have safety. Do you have any consideration on that?
Yes, that's a very good question. So for the capacitors, yes, right now I'm using ceramic capacitors for the demonstrations. But if you like in medium voltage application, you can physically separate them because capacitor is formed by two parallel plates. So you can change the ceramic capacitor to like just two physical parallel plates, like using PCBs. So in this case, you don't have the contact, and it will serve like similar to the transformer isolations.
Thank you. Following up this question, for the medium frequency for medium voltage transformer, the size actually is not limited by frequency, it's more by the isolation creepage requirement. I assume that for capacitive isolation, you would have a similar issue.
Yes. So if you consider about the creepage and clearance, yes, that will be the same. But in terms of the component insulation designs, because transformer normally have like more complex geometries, which is harder to address the insulation designs. But for capacitors, because it has the benefits of like two parallel plates, you can easily just increase the distance to address the insulation design. So in terms of insulation design, capacitor isolation is simpler than the transformer. But in terms of creepage and clearance, yes, they're the same.
Okay, thank you. Excellent work.
Thank you.
Hey, Alexander Conkey from Huntington Ingalls. I'm kind of wondering if you've considered bidirectionality at all with this, specifically in comparison to like a dual active bridge.
That's a great question. I haven't done that yet. But because this is currently we're not dealing with synchronous devices, it's a diode, so it doesn't have the bidirectional capabilities. But yeah, it's definitely like a very valid point to explore in the future. Thank you.
Master Balaprint, you can't increase the distance in the capacitors between the plates. You lose to your capacitance. That's not the solution. The solution is X capacitors, basically safety rated capacitors, which are much bigger and will present a much more difficult job for interleaving them, the cancel the current. So just so you know.
All right. Thank you.
Hi, this is Bokang from ABB. So I have a question. So what's the most motivation for using this SEPIC topology? So it's because of the like capacitance, or it's the capacitor, or it's kind of you're considering the efficiency, or it's about like the compactness. What's the most motivation?
So first is so we're considering capacitive isolation, so which already eliminated a lot like topologies. And second is it has to have step up and step down capability at the same time with wide input voltage range. So which is kind of difficult to achieve by the transformer based topologies. And so, and by doing loss comparison, basically we narrow down to a resonant SEPIC converter.
Okay, so since you also mentioned like high, like it's compact, so what's the size or density compared to like an inductor based topology?
So right now the so for the capacitor itself, it's much smaller than transformer base if you compare just to just the isolation component itself for 5 megahertz. But because this design is it's only 2 layers, and so they have a specific requirement for all the components to be on the same same side. So this makes the converter is slightly larger. So if you can fold the converter, and then this will be a very small converter and smaller compared to the transformer based converter.
Okay, thank you.
Thank you.
Okay, thanks for the great questions. Due to the time limit, then we have to move on to the next presentation. So this afternoon, we will have lab dialogue section. So please come to the lab, and if you have more questions for Ning or other presenters,